Hi, my name is Brandon Shannon, and I want to thank you so much for coming to my presentation today. A little bit of background about myself is I started beekeeping in 2017. I went to the University of Central Florida, where I was the teaching assistant for the Honeybee biology and beekeeping course. Now I'm getting my master's degree from the Ohio State University while doing research with Dr. Reed Johnson on honeybees and adjuvants. So that leads me into our talk today, the toxicity of pesticide adjuvant tank mix combinations to honeybees. So let's get started. So we'll start with honeybee almond pollination, which is really essential to the almond industry and also the commercial beekeeping industry, because 80% of the nation's bees are transported to California for this pollination. And honeybees are the main pollinator of almonds, and this is the case because other pollinators have not really started their activity yet because almonds bloom so early in the year. But unfortunately, there have been a lot of unexplained bee deaths that have been reported during almond pollination. One possible thing that we think this could be is pesticides and pesticide tank mixes more specifically. So tank mixes are combinations of insecticides, fungicides, and any other pesticides that are all combined into one tank so that an applicator only has to spray the almond orchard one time. It only has to pass by one time instead of refilling the tank and spraying it multiple times with multiple different pesticides. Another thing that's often added to tank mixes is adjuvants. These aren't just used for almonds, this is really applicable to all crops, and they improve the pesticide mixture in a lot of different ways. One is better mixing so that your mix mixes uniformly and not you don't get this goop like in this picture here. There's also spreaders and stickers that give you better spreading on the leaf and less leaf runoff. So you see here in the picture on the right, you have water droplets without an adjuvant that just kind of form droplets on the leaf and don't really soak in. But with an adjuvant added, they really spread on the leaf, which allows for the absorption of these pesticides into the plants. And they also can decrease drift in some cases, which will decrease your impact on non-target organisms like fish or other vertebrates. So let's have a look at some of the adjuvants that are applied during almond bloom. So here on this graph, you can see on the x-axis, it's listed by year, and on the y-axis is the thousands of acres that are treated during the blooming period. And you can see each adjuvant is represented by a different color. So that'll kind of show you the wide diversity of adjuvants that are being used and how common it is becoming because there seems to be kind of an increasing trend in adjuvant usage over time. So that leads us to the question, are adjuvant sprays toxic to bees? First, are they toxic by themselves? Do they have inherent toxicity? And secondly, are they toxic in pesticide tank mixes? Because that's really where they're being used, is in the tank mixes. So we're going to try to figure this out by spraying bees with adjuvants. And our methods for that, first we're going to collect a frame of brood from a hive. We are going to brush the bees into a cage every single day. So all of the newly emerged bees will be brushed into a cage so we always know how old they are. We're going to age them to 3 days old or 3 days emerged. And then we're going to knock them out with CO2, carbon dioxide, which will anesthetize them, kind of put them to sleep. And we will spray them with different treatments of adjuvants at different concentrations. And then once they're sprayed, every 24 hours, we will count the number of dead bees that are in each treatment. So by doing that, we'll determine the mortality of each treatment. So our experimental setup will look kind of like this. You'll have your bee, you'll knock it out with CO2, and you'll put it on a petri dish and put it into what's called a Potter tower. So the Potter tower, you put a toxin or pesticide or adjuvant into the test tube at the top, and then it will spray down onto the bees that are on your petri dish, and then you'll be able to determine how many bees are alive and how many bees are dead. So there's some pictures. There's a picture of me spraying some adjuvants into this test tube here. And then the adjuvants will form a spray by the Potter tower into little droplets and spray down onto the bees in the petri dish. So once we have determined how many bees were alive and dead after each treatment, we are going to analyze the data with a dose-response curve. So a dose-response curve always has, in the x-axis, concentration. In this case, we express it as multiples of application rate. Now the application rate is what the manufacturer requires you to use on the label. So 1x would be what the manufacturer requires, and 2x would be double that. And then on the y-axis, we have percent mortality, so the percent of bees that were killed. Here we have Mustang Max, which is our positive control, which means it's known to kill honeybees. So you can see that at 1x, the recommended application rate, you have 100% mortality, and with no Mustang Max applied, you have almost zero mortality. So to compare different treatments, you will determine the LC50, which is the lethal concentration required to kill 50% of bees. So that's determined by the computer, and it does it kind of like this. It makes a little line, and then it draws a line from the 50% mark and draws it down. Let's draw it down to the concentration, the x-axis, to determine that for this treatment, you need 0.20 times the application rate in order to kill 50% of bees. Now, a lower LC50 is going to mean that the treatment is more toxic because less is required to kill bees, and a higher LC50 would mean that it is less toxic because it takes a whole lot of that treatment to kill 50% of the bees. And then additionally, our R-squared value is how well that line fits our points, and the LC50 is 0.20, which is determined computationally. So let's look at some of the adjuvant treatments that we tested. First, we have Surf 90 adjuvant with an LC50 of 5.4. Next is the kinetic adjuvant with an LC50 9.4. Next is the induce adjuvant with an LC50 10.9. And next is the cohere adjuvant with an LC50 29.1. Now, the names of the adjuvants are just the trade names that are given by the manufacturers. So that's where those names come from. But what we want to look at is the LC50. So we can compare these treatments by the LC50, and we can say that Surf 90 is going to be the most toxic because it has the lowest LC50, and cohere is going to be the least toxic because it has the highest LC50. So let's do some pesticide treatments with just the pesticide by themselves. So Vanguard fungicide, we saw almost no mortality even at 100 times the application rate. And Tilt fungicide, we saw some mortality, but the LC50 was 37. And Intrepid insecticide, we saw almost no mortality even at 100 times the application rate. So for Vanguard fungicide and Intrepid insecticide, we were unable to determine the LC50. All we can say is that it's greater than 100 because that is the 100x because that is the highest concentration that we tested. So now let's take a look at the adjuvants combined with the pesticides. So to remind you, here's our kinetic adjuvant with an LC50 of 9.4. When we combine kinetic and Vanguard, I'll remind you Vanguard's LC50 was greater than 100. It was so high it could not be determined. When combining them, the LC50 was 4.0. With Tilt, which had an LC50 of 37, the combined LC50 was 4.6. And with Intrepid insecticide, the LC50 was greater than 100, but when combined, the LC50 was 5.1. So as you can see, the LC50s are significantly lower than in the tank mixes than they are with just the kinetic adjuvant, which means that they have increased toxicity when being used in a tank mix than when being applied by themselves. So in conclusion, we have determined that some adjuvants can be toxic at near application rates, and that adding certain fungicides or insecticides to these adjuvants in a tank mix will increase the adjuvant toxicity. And lastly, the dose makes the poison. So as you can see here, there are different application rates for different adjuvants. And we noticed a trend that the adjuvants with a higher application rate are more toxic or have a lower LC50. So for Surf 90 and kinetic, it's easy to see that there is more adjuvant that is recommended to be added per 100 gallons than there is for the less toxic Cohere. I'd like to thank my advisor, Dr. Reed Johnson, as well as graduate students Emily Walker and Dylan Rickey, my wife Elizabeth Shannon, and the Almond Board of California who provided us with the funding to complete this project. That's it for my presentation. If you have any questions, feel free to email me at shannon.325@osu.edu. Thank you so much for attending my presentation, and I hope you enjoyed it.